Answer the following questions involving the stoichiometry and the thermodynamics of reactions containing aluminum species. Here's the first one. An electrolytic cell produces 235 grams of aluminum according to the equation above. A, calculate the number of moles of electrons transferred. So basically on this one, we're just kind of a thought process. We're going to go from 235 grams of aluminum metal to moles of electrons. Um, and so I would just go 235 grams of aluminum. Okay, the mole is the most important concept in all of chemistry. So I go to the periodic table and I have 26.98 grams of aluminum in 1 mole of aluminum. And then now we got to come up here, and here's the aluminum. And so if you kind of look at the half reaction, we got 2Al2O3. I'm just doing this because you can see that aluminum is over here. The charge is 0 because it's an element. And so very interesting. Aluminum has a +3 charge, +3, but then you have 2 of them, and that's +6. And then +6 times 2 is 12. So if you want to think about it, um, for every 4 moles of aluminum, you get 12 moles of electrons. Now, obviously, um, because I'm just looking at this equation, but 12 to 4 is the same thing as 3 to 1, because basically aluminum with a +3 charge on this side, if you don't pay attention to it being balanced, is going to a 0 charge over here. And so you'd have to add 3 electrons. So you could do 1 to 3 or 4 to 12. They're the same thing, but if you do that, you get 26.1 moles of electrons. And because this cancels this and this cancels this, and you're good. All right, next question. A steady current of 153 amps was used during the process. Determine the amount of time in seconds. I would just take your answer from question A, even though I don't think the sig figs will be right. They just, you have 26 moles of electrons. Well, we know and that there's 96,485 coulombs. Let me grab this baby eraser per mole of electrons. So now we're in coulombs. And then 153 amps is 153 coulombs per second, because amp is a measure of current and current is charge per unit of time. And so the 153 coulombs would go here and the seconds would go here. And then it says determine the amount of time. And so when I did that, my calculator says my answer I put down, I didn't round here. I just kept this 20, whatever the answer for A was still in my calculator. I just didn't hit clear. But anyways, when I did that, I got 16,478.41902 seconds, which has way too many sig figs. And so 16,500 seconds is the best answer for this problem. Now, this one's interesting. Why? Because it wants to know the volume of carbon dioxide. Now, I'm going to go back to slide 1 and show you that basically this is not a thermochem. I just want you to look on the right here. We got 4 moles of aluminum metal because it's hot enough that it's liquid. So metal in liquid state, and 3 moles of carbon dioxide. And I'm not really looking at the other side, but if we come over here, you can see that on this side there's a 4. So there's stuff over here. I'm too lazy. It's on the first thing. But there's a 4-to-3 ratio on the product side between aluminum and carbon dioxide. And so this question is, um, how many liters of this would be produced? Well, this would be 100, what is this? 235 grams. And and then the molar mass is 26.98 grams per mole. And then the first thing I'm going to do is I want to figure out how many moles there is of this. And we would call this, back last year in chapter 5, when you guys were doing the gas laws, this would be called a mass mole problem. So this would be step 1, this would be step 2. You'd use this 4-to-3 mole ratio in step 3, and then you'd be done, because if this is a mole, we don't need to know the molar mass. So the first part of this problem is you do 235 grams of aluminum, and then there's 26.98 grams of aluminum in 1 mole of aluminum. And then from the stoichiometry, you can see that for every 4 moles of aluminum, you only get 3 moles of carbon dioxide. And then this cancels this, and this cancels this, and I'm going to keep all the sig figs, 6.532, 616, 753 moles, keep being obnoxious. All right, now I'm going to come up here, grab this, move down. Probably should extend the page even right now. So now I'm going to haul out this bad boy, which is PV equals nRT. And we're going to solve for V, because it says in 3, flipping my paper over, calculate the volume of CO2 measured at 301 K and 0.952 atmospheres. So we got V equals nRT over P. Well, N is up here, 6.532 dot, dot, dot. It's still in my calculator, moles. And then times 0.0821 atmospheres times liters over mole times K, and then times 301 K. And then the pressure is down below, so 0.952 atmospheres. Sorry, I'm out of room. Atmospheres cancels with atmospheres, K cancels with K, mole cancels with mole. I put this in my calculator. It says 169.574241 liters, and then I only get 3 sig figs, so the best answer is 170 liters. D, for the electrolytic cell to operate, Al2O3 must be in the liquid state rather than the solid state. Now, guys, we just did an electrolysis lab. And remember now, in our lab, we had the copper in here. They're in the same cell. You hook up the battery. The stuff can move. The ions in solution can move. But the important thing is that for electrolysis to work, the charged species have to be able to migrate to the right electrode. Otherwise, electrolysis doesn't work. And so this is just what the scoring guidelines say. I'm just going to write it down, but I just want to talk about it. Al2O3 is an ionic compound. Ionic compounds have a strong force of attraction, because of Coulomb's law, and so ionic compounds tend to be solids. It's an ionic compound. In the solid state, even though it has charges, it will not conduct electricity. So in order, again, this is right off the scoring guidelines, in order for the cell to operate, Al2O3 must be in the liquid state, or you need to melt it or molten, whichever word you prefer. So I'm just going to come down here a little bit. Oh, look at that. You can see who put stuff on Facebook. Um, and I'll grab this Al2O3. Where was I? Must be in the liquid state. So that the ions can move to the electrodes to react. So remember, redox equations is the electrons come down on either the cathode or the anode, and and where the liquid touches the electrons and the solid is where all the chemistry occurs. All right, now this is crazy. When you get to question 5, it's a whole new equation because see how they like it goes over, it's not an ABC. So now we have a different equation with a different aluminum species, and it says when ALS is placed into a concentrated solution of KOH, the reaction represented below occurs. So when you put aluminum into KOH, which is a strong base with water, it's called a complex ion. They took them off the test. Now we want to do the voltage, and this is really how it looks on the new test in that they give you the part of the chart you need. So if you look, oops, I went up too fast. Notice this equation has aluminum on the right. We need aluminum on the left with the 2 in front of it. So I'm going to take this first equation and flip it. So 2ALS plus 6, sorry, and I'm doubling it, plus 8, not add, but multiply, OH minus goes to 2AlO4 minus plus 6 electrons, because notice we doubled everything. So there's a 2, there's an 8, there's a 2, there's a 6. We don't multiply by the 2, but we do flip it. So this is positive 2.35 volts. Okay, now this one, so now notice this is in the right place and this is in the right place. So now we got to get the H2 in the right place, and the electrons got to match. So this equation has a 1 H2, but we need it to have a 3 H2. So I'm going to take this same equation and triple it. So I have 6 H2O liquid plus 6 electrons, which is great because we need those to cancel. Goes to 3 H2, which is great because we need a 3 on that side, plus 3 OH minus, sorry, not 3, we're tripling it. So this is a 6. Sorry, let me grab that eraser. Come on, I don't want the eraser anymore. All right, so then plus, I get to triple this, so 6 OH minus, but even though I triple it, I just leave this alone. So E naught is negative 0.83 volts. And so what happens is I have 6 OH minuses here and 8 here. So there's a 2. So now it matches. And so I got 2 ALS plus 2 OH minus plus 6 H2O on the left. And on the right, I have 2 of these. I can't remember what that's called. Aluminum hydroxy something. And then 3 H2. But the question is, we're not done yet. Oops, I hate when I do stuff like that. Sorry. The question was, what would the voltage be? And the voltage is going to be 1.52 volts because 2.35 volts plus negative 0.83 volts is 1.52 volts. All right, and then the last thing is calculate G naught in kilojoules per mole. It actually should be moles of RXN. I just couldn't figure out how to do this in the SmartBoard software for this for the formation of, probably should be a 2 there. Actually, no, there shouldn't. It was just, this shouldn't be there. So what is the heat of formation for that reaction? And And so delta G naught is equal to negative N F E naught. And so we have negative 6 moles of electrons times 96,485 coulombs per mole of electrons times 1.52 volts, which is joules per coulomb. So this cancels this, and this cancels this. And then I always like delta H and delta G to be in kilojoules. So they actually asked for kilojoules. So 10 to the third joules is 1 kilojoule. And you end up with going to 3 sig figs, negative 880 kilojoules. And I'm putting a dot there because that 0 is significant. Or kilojoules per mole RXN, because those things are interchangeable.